Hello everyone. This is going to be a one single pass through, no post editing version of Lecture 19, the first one I'm doing. I'm up against deadline, so this is going to be a little rough. I'm going to try and keep it to less than 10 minutes. I probably will fail in that because I've got a lot to tell you, lots of things about this process as well as this particular lecture. Okay. So here's the old version of the reading quiz, just as you're used to seeing it in class. You've done the Moodle version, which looks a little different from this. Hopefully it's the same. I've tried to be real careful importing these things. But I'm going to go, I know you've already done that first quiz, and Moodle self-grades it for you. But I'm going to do it here as well so that I can talk about the implications of this quiz. You know from this... from the Moodle grading that the correct answer here to number 1 is C. The total net current enclosed gives you the line integral of the magnetic field around a closed path. Okay, so that's the integral of B dot dl. That's mu naught over I enclosed. So that has, that's not a very nice integral, is it? Okay. That looks just like Gauss's law for a surface integral of E dot dA. A surface integral of E dot dA is Q enclosed over epsilon 0. So there's a closed line integral here. There's a closed surface integral here. It's the current enclosed. It's the charge enclosed in the volume. The current enclosed in that loop. Okay, come back to that more in the lecture. The correct answer to number 2, using Ampere's law, the integral must be evaluated, has to be around a closed path. Okay. Now remember all of the generalities that we talked about for Gauss's law for the electric field. We said that we only used it in simple cases using a lot of symmetry and around some very special paths. Okay. But you don't have to use a circular path. The first example we're going to use, and many of the samples we use circles, but it's an arbitrary closed path. So that's the story there. Okay, now I'm going to try and go through the lecture in not full 50-minute style. I'm going to take less time than a full lecture to just hit the high points of this material. Before I even start section 28, I want to kind of give you a preview of an introduction to this thing. You remember when we talked about the electric potential in previous chapters, we said that the electric potential difference between 2 points A and B was the integral of E dot dl from A to B. Where did that come from? That came from what you're supposed to remember from Physics 111 about the definition of work potential energy in terms of force dot distance. Okay, this is electric potential energy. This is the electric potential, which differs by the charge. Okay, if you remember what we did in mechanics in Physics 111, we talked about particles moving in a plane in an XY plane. And we said that if we went from a point A to B and then back to A again along a closed path, that potential difference, work potential difference, was 0. It's the same thing here for the electric field. So we've shown that for a closed path, the integral of E dot dl is 0. We're going to generalize that because this is strictly for electrostatics. That's the condition there. And I've already mentioned in the notes there this law for Gauss's law. So do something similar for the line integral of B dot dl, and that will lead to Ampere's law. Okay, that's the next section here. What is Ampere's law? Ampere's law is this. It's the integral of B dot dl is mu naught I enclosed. Closed path and closed circuit theory. You remember one of the other surface integrals we have done so far. Integral of B dot dA is 0, and that's saying that there are no monopoles. Gauss's law says that integral of E dot dA is Q enclosed. Integral of B dot dA is 0. So look, here's where we stand right now in terms of electrostatics. We have partial pieces of Maxwell's equations. We have 2 line integrals and 2 surface integrals. We have the integral of E dot dA, which says that the electric field is conservative for electrostatics. There's another term here, which is going to be Faraday's law. And the integral of B dot dL is mu naught I enclosed now. That's the new material. Okay. Previously, a surface integral for E dot dA is Q enclosed over epsilon 0, and we know this one. Okay. Notice that here's a source term, here's a source term. The source term for electricity is up here. It's a volume integral. This one is a line integral here. Note the crossing of those terms. Okay. All right. So let's do a very simple example. Let's look at the application of Ampere's law to a straight wire. Okay. Here's that current going through a loop, and there's a vector stroke missing there. Integral of B dot dL is that. Invoke the normal symmetries just as we did in the Gauss's law for electricity. We take a closed path, which is a perfect symmetry circle, has perfect symmetry, which is a circle. We know from the right-hand rule that the B field, if I put my thumb in the current direction and wrap my fingers around the wire, the B field makes circular closed paths. Okay, so that makes the integral of B dot dA very simple to evaluate for that. The dL along the path is exactly parallel to the, so that integral just becomes, the B comes outside at all, since the distance is the same everywhere along here, that distance r times 2 pi gives me the circumference of the circle, so I get that, and I get B, which is the answer we came to before. Okay, I'm doing this real fast, folks. Okay, we're up to 7 minutes, I see now. We can apply these to not only magnetic fields outside the wire, okay, we can go inside and outside as well, okay. So here the current is going that way. I take a closed loop inside or a closed loop outside, okay. If I take the closed loop outside, that's the previous calculation. If I take a closed loop inside, okay, I get a smaller, I get a different amount here, okay, depending on whether how much current is inside the loop. And I'll have to have you go into detail using that from your notes, okay. Here is a really important example. Here's the magnetic field inside a solenoid, okay. A lot of you are in allied health fields, okay, so you're around MRI machines. MRI machines have a big solenoid in which you put your body to image things, and that device is called a solenoid, and I wrap a bunch of turns around a core, a volume, and I get a magnetic field that goes like that, okay. The calculation of the electric field in the solenoid is actually very simple, okay, because here's a cut through that solenoid, and I take a path that looks like this, okay. I take a path and go around here. Inside the core, the magnetic field is strong. Outside, it's zero. Remember that argument we talked about when I wrapped my wire and mapped a half plane into another half plane? So the B field is uniform and constant inside there. Okay, it's zero out here. In here, what fringing fields they are perpendicular to the path for the most part. Okay, so this integral simply becomes those four terms. Those go to zero, and this one survives. That's that one there. Okay. Okay. So there's the simple result for the magnetic field. I'm going to stop there. I'm already up to 9 minutes. Okay, I realize in doing this that I'm going to have to get better about summarizing these things and hitting the higher points. When I get to later sections, I won't even have as much time as this. So I'm going to pause here. No, I'm not going to pause. I'm going to stop and invite your comments to how this how you think this is going. So, end of lecture.